The basic premise is based on a frame of reference coordinate system that works like the compass, right? Compass rose. And so if you think about your traditional graph set, this would be considered 0 degrees. And then we measure around counterclockwise to 360 degrees. As such, straight up and down is 90 degrees, straight backwards is 180 degrees, and straight down is 270 degrees. The point being that if you are given two vectors, vector A and vector B, right, we should be able to say what direction they are pointing in comparison to the compass rose, which allows us to compare them to each other. The key there will be that this is pointed at a particular angle theta, right? So let's say that A in this particular example is pointed at some theta that looks like this, right? Then theta would simply be this angle from here to there, right? In the first quadrant, the angles will correspond to anything between 0 and 90 degrees. If B is not between 0 and 90 degrees, then those two things do not generally point in the same direction. So if I have a different vector B going out like this, right, then all the way over would be phi for that particular angle, sorry, phi. Which means that it has to be between 90 and 180 degrees. The key there is that, especially on standardized AP tests, they may say things like B is offset 30 degrees from the vertical, right? And so they are indirectly telling you that it's in the third quadrant. Go ahead.
How do you know if it's, what's the difference between B and like a cube? If they said that, how would you know which direction it is?
I'm sorry, I missed the first part of your...
If it's 10% off the 90-degree angle, is it 100 or is it 80?
Well, so that you're right. That's right. So you need to read for context. So a lot of times what they'll say is they'll say things like it's 10 degrees offset from the vertical, or it's 10 degrees offset from the normal, right? Or it's 10 degrees offset from the horizontal, or whatever it will be. Sometimes they'll use...
Can it still be both ways, though?
It could be, yes. And so you need to make reference to what else is happening in the problem, right? But a lot of times it will be more specific, like it'll be 10 degrees off of south, and it could be either this way or that way, and then you'll have to say, is it 10 degrees right of south or 10 degrees left of south? But a lot of times they'll be specific. But if it's not listed in reference to another direction, right, and it's just told to you at a particular angle, then the angle is always referencing from 0 around like this, always. That's standard for all physics concepts, for all physics texts. So if A is at 30 degrees and B is at 30 degrees, then you agree that those two things are in the same direction. Whereas it's possible, like in a math class, where they would say something like this angle is 30 degrees, this back angle back here, right? And they would say B is 30 degrees also, but that's not actually the direction of B in this particular example. Does that make sense? Okay. The key for understanding vector addition goes back to your basic concepts of vectors, right? If A and B were simply forward, right, parallel like this, then we know that the summation of A and B is from where A starts to where B finishes, right? And so it's just a long vector like that. But if we had vectors where A was this way and B was this way, right, the summation of those two is not a vector that's the same length as these two things. This is because this one is negative and this one is positive. And so if I think about it as like this one is positive 7 and this one is negative 10, then the summation of those two things is to draw the first one and then without lifting my pen, draw the second one backwards from where I started, leaving a distance from where I start to where I finish as a vector that points in the negative direction, which you can tell me already is -3. Parallel vector analysis is relatively straightforward in terms of calculations. We do that instinctively. But something that I did there that's really important is this concept of drawing the first one and then without moving, drawing the second one. And then the difference between the two is the overall result, right? Whereas if I drew this one and then I drew that one just like this, I don't get much information out of it, even though instinctively we know that the answer is -3, right? And so this is called head-to-tail addition, right? Head to tail. head-to-tail addition. If A and B are perpendicular, then we've already seen that we would draw A like this, and let's say B is like this. Then the combination of those two things is not this and this, right? That is not the answer. If I draw it head to tail, I draw this one first, and then without moving my pen, I draw this one second. And then my answer is from where I start to where I finish as a vector on a triangle. Because if I move 10 paces east, and then I move 10 paces north, I may have traveled 20 paces as a distance, but as a vector displacement, it's 10 squared square root to get this hypotenuse going across there. That makes sense? This is the ultimate goal of non-perpendicular vector addition. We're going to take A and B that are at some weird angles, figure out what the overall component in the x direction is, what the overall component of the y direction is, and create this triangle that is perpendicular from these two vectors that were not at the beginning. The basic step process has what I think is 3 steps. First step is to resolve the givens into perpendicular vectors. This process we've done before, and this is essentially this process right here backwards. We did this with projectiles, where this was my initial V naught at some angle theta. I use this V naught and theta and my trig functions in order to find Vx and Vy naught. This process, resolution, vector resolution, can be accomplished for any vector, whether or not it's velocity, acceleration, momentum, etc. Right? And so that's the first step. And the key to doing that, right, or the reason why we do that, is because then these vectors end up matching a frame of reference that I can assign positives and negatives to, so that I can do a simple addition that's straight on in parallel frames. Right? So first step is resolution. Second step then is to add the components based on that frame of reference. Where we're actually going to use our positives and negatives. The key to this step is recognizing that what we're working on then becomes linearized, because we only care about just the y components and we only care about just the x components when we're defining positives and negatives. And so what we could say is that A has a component of x and a component of y, and B has a component of x and a component of y. And so we will add ax and bx together, and we will add ay and by together, right? And then the third step is to take that final solution, right, the perpendicular addition of those components. Components. Ooh. In other words, Rx plus Ry equals R, written as vectors like this. R is taking the place of the answer from the vector resolution. When I take vectors, I resolve into components. This is a vocabulary word. This is a vocabulary word. Vector resolution is the act of resolving components that are perpendicular according to the xy coordinate axis. The answer from that, which is, if we think about it as the original here, is the resultant. That is a weird way of saying the result. The resultant, T-A-N-T, right, is the answer for adding perpendicular components. And we call this a resultant as opposed to just the result, because it's not just whatever this number is plus whatever this number is. It's the triangulation of those two vectors in order to find the hypotenuse. Right? Once I have this, then all I have to do is list this resultant as a vector, which means that it has both magnitude and a direction given in degrees according to the compass rose that we started with at the top. And so we're taking two vectors, breaking it into perpendicular x's and y's, and then putting it back into one vector that may not align with x or y. That make sense?
So, what's the difference between the R and the B?
I'll show you. Probably easier to think about it in terms of an example. So, the example I have is A as a vector equal to 75 on an angle of 110 degrees. Now, I've generalized in terms of a vector, so I haven't given this units because A could represent any vector, acceleration, displacement, velocity, or momentum. And then B as a vector is given as 100 meters per second, or sorry, no units, at 300 degrees. And so right off the bat, if I just took this and thought about it holistically, right, then A at 110 degrees, this is 0 degrees, 90 degrees, 180 degrees. 20 off from 90 is A, and it looks like that. Right? In this case, A is 75. B is 100, but it's at 300 degrees, right? So 270 degrees is straight down, so offset from the angle here is B. If I'm being careful about it, this one is 75, that one is 100, so this one is slightly shorter than this one. And then the given angles are always referenced from the original 0 degrees around like this. So this angle is 110 degrees. And then, let's do it inside. This angle is 300 degrees. It's easy to make the mistake of thinking that these two things are in opposite directions because it's hard to actually draw 20 degrees and 30 degrees accurately. And the key is, because we're going to use geometry to solve these, it doesn't have to be perfect, right? But you do want to give yourself a good sense of what's happening in the sense that this is in the second quadrant, this is in the fourth quadrant. The majority of what's happening here as a vector addition, A plus B, is actually going to cancel out. Because up and to the left plus down and to the right is probably going to yield mostly nothing, right? Right. In order to get started then, right, the first thing we're going to want to do is think of these two things as separate items, right? As you get better at this, you're welcome to do all the work on one diagram. But what I like to do is then take them and look at them individually, right, on two separate pictures because it keeps the work neat. So if I redraw my axis here, and I redraw the second axis here, I list A like I just did, up like this, and B down like that. I know that B is 100, and I know that A is 75. And then based on this diagram, I'm going to find a useful angle that I can draw a triangle around. Right? So at 110 degrees, I can't draw a triangle around 110 degrees that draws x and y components. But what I can do is choose just this section of the 110 degrees. Right? Because I know that from here to there is 90 degrees. That tells me that this, which I'll call an internal angle, is only 20 degrees. And then the same down here for this one. I know that from here to here must be 30 degrees because the overall is 300, right? And so again, I'm finding an internal angle, which is 30 degrees. We'll operate on these two individually. But the goal is the same. Each vector represents two directions, both x and y. And so what we want to do is we'll want to draw this as a resolution into those x and y directions, right? And so the best thing that I preach a lot in Physics 1 is that you should be able to say the words as you're drawing the head-to-tail addition, right? And so 75 points up and to the left. And so if I draw my y component starting at the axis vertically upwards, then this would be what I call AY. Without moving my pen, although I'm going to shift and use a new color, from the head of that vector, I'm going to draw the x component ending where my original ends as well. This would be AX. These two things are perpendicular to one another, and thanks to the 110 degrees, I know an internal angle of 20 degrees. So again, I'm starting with my original vector of 75 at 110 degrees. I'm saying to myself up and to the left, and I'm drawing in AY up, AX left. Right? They should fit together. It's possible that you could absolutely draw AX first, left, and then AY second, up, and then utilize what you know about this 20-degree angle to say that this is 70 degrees down here, and operate on the triangle below. Thanks to the trig functions, it'll work either way, and however way is convenient for you. It also can be convenient depending on how the diagram may look in the original picture. Right? If you have two of these that are relatively separated, you could choose either side triangle to resolve. But a lot of times if you had, say, B going this way, it might be useful to resolve the vectors that point right and up and left and up, just so that they separate out on the picture. That's completely dealer's choice, but it's good practice to be as organized as possible so that this information doesn't get confused as you go down through the system. Make sense? All right, so then, of course, it's out of focus. I feel like that AY is not right. There we go. That looks better. All right, so, of course, then you can use your trig functions to find AX and AY based on the triangle. Right? And so in this particular case, we'd say that AX is equal to 75 times the sine of 20. And we'd say AY is 75 times the cosine of 20. I have those numbers as AX is 25.7 and AY is 70.5. Now again, you would get these same numbers if you use the other side of the triangle, because the trig functions would flip and the angle would be 70, and those things would work out because they're complementary, right? All right, so that tells me what AX is, and that tells me what AY is. Now, this is in magnitude only. We have not applied a frame of reference yet, right? So this is still a vector resolution from step 1. That make sense? Okay, so then on the second picture, we do pretty much the same thing, right? This one points down and to the right, and so I choose to draw along the axis down, and I call this BY, and then I choose to draw to the right to close off the triangle. This is BX. You could accomplish the exact same thing by drawing BX and then BY, as long as you draw them head to tail. Draw the first one, then draw the second one. Either way, that yields a perpendicular 90-degree angle with an inside angle that you figured out from the original setup. That allows me to figure out what BX and BY are based on this triangle. So BX is equal to 100 times the sine of 30, which I have as 50, and BY as 100 times the cosine of 30, which I have as 86.6. All of that is step 1, and is by far the most important part in organizing what you're doing. Right? Make sure you draw a very careful diagram that lists the vector according to the given, and then make sure you draw in the components perpendicular head to tail. If you do that organized and you keep the AXs and the BXs on top and the AYs and BYs on the bottom, usually that should be a good start. All right? So then step 2 is to add them according to a frame of reference that isn't the compass rose, but is instead up is positive Y and right is positive X. And so all I'm basically doing is taking these numbers and assigning positives and negatives. Right? I'm not changing much about it. So I'm going to say that AX points left. So this is actually negative 25.7. I'm going to say that BX points right. So this is actually positive 50. Now, of course, you don't have to write the positive sign, but I do because it reminds me that I've actually assigned the direction before I move on. Then, of course, a Y is up, and so that's positive 70.5, and BY is down, so that's negative 86.6. Once we have this, then it's just a matter of adding your X components and adding your Y components to get what we would call the components of the resultant, right? This yields, as an addition, 26, negative 26 plus positive 50 as Rx, which is the vector solely in the X direction of the answer, right? So in this particular case, that would be 24.3. Positive. Whereas AY plus BY is positive 70 plus negative 86, so RY is negative 16.1. This is the beginnings of an actual answer because now we've actually added A plus B to get R, right? But we've only added the parallel components. We haven't actually completed the entire diagram. So when we move into step 3, right, we're going to add the perpendicular components, which is what we started with. So Rx is a positive value, which means that it points to the right at 24.3, and Ry is a negative value, it points down at 16.1. Now again, these are X and Y, so they are perpendicular. So I need to do the perpendicular addition. I'm going to draw 24.3, and then without moving my pen, I'm going to draw 16.1. This is 24.3, which is my Rx. This is negative 16.1. Now at this stage, the negative is fairly irrelevant because again, this is just the side of a triangle, and we're going to do a squared, b squared, c squared to get the hypotenuse. But what is key is that my answer, right, is from where I start to where I finish as a vector addition. So this is R, is the resultant and ultimately the final answer. So of course the first thing I'm going to do is a squared, b squared, c squared to get R, right? And so if I do that, R is the square root of 24.3 squared plus 16.1 squared, which I believe is 29.1. This is the magnitude of the hypotenuse of our answer. Now the direction is always tricky because again, just finding theta inside the triangle does not tell me that this is in the fourth quadrant, right? So the first thing I tend to do is I tend to identify an angle that matches up to the axis as opposed to one away from the axis, right? So down here at the tail of R so that I can reference that compass rose picture that I started with at the top. So if I call this theta, right, I can solve for theta using the trig functions. Now I can do that with any one of the numbers that I have, right? And so it doesn't really matter, but I tend to use tangent because these values were calculated prior to R. So I would say the tangent of theta is equal to 16.1 divided by 24.3. Again, the negative sign is irrelevant because this is just a magnitude, which gives me a theta of 33.5 degrees. But 33.5 degrees is not the direction of R, because 33.5 degrees is in the first quadrant. And so I need to be a little bit smart about what's happening. If I think about the axis, right, 0 degrees is over here, and the angle is all the way around like this. Let's call that phi. There are a number of ways to think about it, right? One is to think about it as 270 plus 90 minus theta, whatever this space is here. Another way to think about it is if I took this all the way around, I'd be at 360 degrees. So if I take 360 degrees and go back theta degrees, then I have phi, right? And so in other words, phi is 360 degrees minus theta. So my final answer is the resultant of A plus B is 29.1 at an angle of 326.5 degrees. Does anybody have any questions? The reason why this particular setup and process is so useful is that this could be accomplished with many vectors, right? It's not unreasonable to think that there could be more than 2 vectors added together. And rather than doing this one plus that one, and then this one plus that one, and then this one plus that one, and repeating the process, breaking them down, putting them together, breaking them down, putting them together, it's much easier to take all of them at the beginning, break them into x and y components, resolve into components, add the components as perpendicular, or excuse me, as parallel values in either the x or y domain, and then put them back together as perpendicular things that create a triangle. That makes sense? Okay.